Okay, new topic, summation notation. We can express the sum a1 plus a2 plus a3 plus dot 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 plus an. So if n numbers, we want to add them up. We have the sum of them, and we want to express it in a concise way. We can use this notation. So this is known as summation notation, also sometimes called sigma notation, because this thing here in the middle is the Greek capital letter sigma, which is like our letter S, and the idea is sum, right? It stands for sum. So how do you read this? This is the sum from I equals 1 through n of a sub I. So what it means is start from I equals 1 and do a1. Then move up, make I become 2, and then add a2 to that, right? Add a2 to a1. And then go up, make I go up by 1. So now I is 3. And so now add a 3 to the previous sum. And then keep doing that all the way through n. So the last legal value for I is going to be n. And then you'll add a sub n at the end. And that's the whole thing. So for example, the sum from I equals 1 through 4 of I squared is the following. So again, we start from I equals 1 and we go through I equals 4. So first we have 1 squared plus 2 squared plus 3 squared plus 4 squared, which is this, which is 30. So an interesting thing to note is that what we're really doing here is doing a for loop, right? The above, meaning this example, is like the following code snippet in Java. So we start with sum is 0. It's our variable for storing the sum. And we have a for loop, for into I equals 1. So start from I equals 1, as we see here, I equals 1. I is less than or equal to 4. That's this thing here, meaning go through 4. 4 is the last possible value for I. Sum plus equals, so add to the sum, I to the power of 2, I squared. So at the end of this loop, once this loop is completed, the value of sum is going to be what? It's going to be 30. Okay, so some more details about summation notation. There are some variations that we can do as well. So a typical example, we start from I equals 1, and that's how I first introduced it. But really, we can start at any integer, not necessarily I equals 1. For example, we can start at -3. Nothing wrong with that. And it would just be the same thing. You'd start from I equals -3, so it would be I to the power of -3 plus I to the power of -2 plus I to the power of -1 plus I to the power of 0, and so on, all the way through 8. Another point is that we can use any variable name instead of I as the index variable. We can use, for example, J or K. We don't have to use I specifically. Another point is that there's another style of summation notation, and they can be used interchangeably. So sometimes instead of writing the sum from I equals 1 through n of a sub I, we can write the following. The sum over all I in the set 1, 2, all the way through n, right? So again, I is ranging over this set, the sum of a sub I. Again, the sum of a sub I, where I ranges over the set 1, 2, dot, 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 all the way through n. So for example, the sum over all k in the set 3, 4, 5 of 2k plus 1. So we want to do 2k plus 1, add that up a bunch of times, where k comes from the set 3, 4, 5. So first k is going to be 3, then k is going to be 4, then k is going to be 5. So that is 2 times 3 plus 1, then 2 times 4 plus 1, and then plus 2 times 5 plus 1, which gives us 27. Now, a restriction in summation notation is that the index variable, so this I we call the index variable, or whatever we call it, whatever it is, it doesn't have to be I, but whatever it is, this index variable can only represent integers. So saying something like the sum from I equals 1/3, 1/3 to 1/55 of whatever, That's nonsensical. I can only be integers, can only represent integers. Okay, example. So so here's a sum, and we want to express it using summation notation. So we know an incorrect answer, right? Because if we would try doing the sum from I equals 1/3 through 1/55, that would not be correct, because I can only be integers. So how do we express the sum using summation notation? So there are many possible answers. One possible answer is this: the sum from I equals 3 through 55. So I is at all times an integer, but what we're doing is we're doing 1 divided by I. That's what we're adding up. We're not adding up I squared or anything. We're doing 1 divided by I. Okay, now very, very closely related to summation notation is product notation, also sometimes called pi notation. If we have a product, if we have a bunch of numbers, am plus 1, am plus 2, all the way through an, and we want to, we're multiplying them, so we want to express the product, we can do it as follows: the product from I equals m through n of a sub I. So for example, the product from k equals 3 through 5 of 2k plus 1. So that would be 2 times 3 plus 1 times, instead of not plus, times 2 times 3 plus 1 times 2 times 4 plus 1 times 2 times 5 plus 1. So that's 7 times 9 times 11, which is 693. Now, based on this idea of product notation, we can introduce a new definition, which will become more important when we talk about counting in a future week. So, given a natural number n, we define n factorial as follows. So we write it like this: n with an exclamation point. N factorial is equal to 1 times 2 times 3 dot 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 times n. So you multiply the number starting from 1 all the way through n, and that gives you n factorial. We now know another way of expressing this, right? We can use product notation. So this is the product from I equals 1 through n of I, right? So it's 1 times 2 times 3 all the way through times n. So some examples for factorial. So 1 factorial is 1, 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. Now you might wonder, what about 0 factorial? Okay, so 0 factorial, for technical reasons, we define 0 factorial to be 1. Okay, but we'll see why not this week, but the next topic that we cover, counting. And we don't talk about factorials of negative integers, right? So we're only talking about factorials of 0 or positive integers. Okay, now we can go further with this product and the summation and product notations. So first, before we get to another example, let's take a look at some code. So take a look at this code and try to figure out what is the final value of sum. So sum starts out at 0, and then we do a bunch of stuff with it, and we want to know what is the final value of sum. Try to figure it out. So here's my reasoning. So initially the value of sum is 0. We go through the outer loop 5 times. Well, how do we know that? Because we start from I equals 1 and we go through, right, I is less than or equal to 5. So it's a total of 5 times that we go through the outer loop. Okay. Now on each of those 5 iterations, we go through the inner loop how many times? 3 times, because the inner loop starts from 1 and goes through 3. J starts from 1 and goes through 3. So we go through the inner loop 3 times on each of the 5 iterations of the outer loop. Again, we go through the outer loop 5 times in total, and then on each of those times, we go through the inner loop 3 times. So in total, how many times do we go through the inner loop? Well, it's 5 times 3, which is 15 times. Now, each of those 15 times, we increment the value of sum by 1. So the final value of sum is 15. Okay, now that we've seen this, now let's consider this example. What is the sum from I equals 1 through 3 of, hold on, this is a mistake. So here we have the same idea. Sum from I equals 1 through 5 of the sum from j equals 1 through 3 of 1. So it's really the same idea as what was going on here in this nested for loop. So we can do it like this. So here we have the outer sum from I equals 1 through 5 of, well, what's the inner sum? It's the sum from j equals 1 through 3 of 1. So that's 1 plus 1 plus 1, just adding up 1 3 times. And then so that's in parentheses, and then we have the outer sum still to take care of. Okay, so what I'm doing here is I'm expanding the inner sum, and then keeping the outer sum for now, and then we're going to expand the outer sum. So to expand, well, first let's rewrite it as the sum from I equals 1 through 5 of 3, because 1 plus 1 plus 1 is just 3. Now we just have to do the outer sum. So this is the sum from I equals 1 through 5. So in other words, 5 times I want to add up 3. So 3 plus 3 plus 3 plus 3 plus 3, which is 15. Here's another example, a more tricky example. The sum from I equals 1 through 2 of the sum from j equals 2 through 4 of I times j. So first I'll show you how to do it by expanding the inner sum first. So when we expand the inner sum, what we have is, well, we start from j equals 2, so that's I times 2. And then we have j equals 3, so that's I times 3. And then plus, when j equals 4, we have I times 4. So that's the inner sum. And that's this thing in parentheses. And then we still have the outer sum to do. So it's the outer sum of the inner sum. So now what do we have to do? Well, now we substitute the values for I. So we have I equals 1. So we start with I equals 1. So we do 1 times 2 plus 1 times 3, right? So I becomes 1 plus 1 times 4. I is again 1. Now we're done with I equals 1. So now I goes to the next value, which happens to be the last possible value for I in this case, which is 2. So now we have I is 2. So we do 2 times 2, 2 times 3, plus 2 times 4, and we're adding everything up, and we get 27. Now, an alternative way to do it is like this. We can expand the outer sum first, like this. So if we expand the outer sum first, what we're left with is 2 inner sums, right? So in other words, if we say, okay, we'll start with I equals 1. So what do we have then? We have 1 times j for the inside. But then we also have another possible value of I, which is 2. So then we have the 2 times j sum. So here we have the inner sum being pushed off for later. Again, in this alternative procedure, what we're first doing is expanding the outer sum, and then later we're going to expand the inner sum, which is the opposite of how we did it on top. But we're going to get to the same result. So this is, well, start from j equals 2. So this is 1 times 2 plus, and then j becomes, so again, it's 1 times j. So first j is 2. So it's 1 times 2. Then it's 1 times 3 because j is 3. Then it's 1 times 4. Okay, so that's this sum. And then we have to do this other sum. So we start again from j equals 2. So now we have, but now I is 2. So it's 2 times j. So it's 2 times 2 plus 2 times 3 plus 2 times 4. And that is again 27. Another example. Here we have the sum from I equals 2 through 4 of the product from j equals 1 through 3 of I plus j. Okay, so again, we can do it in 2 different ways. First, I'll show you how to do it, where we expand the inner first. In this case, the inside is a product. Okay, so we're going to expand the product first. So if when we expand the product, we're going to be doing I times the first value of j, which is 1, times I plus the second value of j, right? So it's I times 1 times I plus 2 times I plus 3, and then we still have the outer sum to take care of. So we have to do the sum from I equals 2 through 4 of this. So we first have when I is 2, then I is 3, and then I is 4. So this is when I is 2, and here is where when I is 3, and then plus here is where when I is 4. Adding and multiplying, we get 390. So that's one way to do it. The same example, but with an alternative approach, is where we first expand the adder, right? We first expand the in this case the summation, which is on the outside. And so we first substitute I equals 2. So we have the product from j equals 1 to 3 of 2 plus j, right? Here's where I is 2. Then we do the case where I is 3. Then we do the case where I is 4. So those are the possibilities for I. And now we have to expand these products. So we start from j equals 1 through 3. So it would be 2 plus 1 times 2 plus 2 times 2 plus 3. Right? So that's this product. And then the next product. Okay, and then the last product. And doing the arithmetic, we get 390 again. So it's the same approach. It's a different approach, but it gives us the same result. And now here, interestingly, here's a code snippet corresponding to the example. Okay, so we start with the sum of 0, and we have this adder loop, which is the summing loop, starting from I equals 2 through 4. And then each time we go through the adder loop, we need to do the product, the inner product loop, right? So we start with a product. We start with product equals 1. Now think about why we start with 1 instead of 0. Okay, think about it. But anyways, we go 4 and j equals 1. So here we're doing the product. We start from j equals 1, and we're going to go through 3. Product times equals I plus j. In other words, do I plus j times the previous product. And then once you're done with the inner loop, take that result from the inner loop and add it to the sum, right? The outer loop is saying, okay, whatever you do in the inner loop, add it to me. Anyways, this is code snippet corresponding to the example. If you don't like the code snippet, if it doesn't make sense to you, don't worry about it. It's the only reason I'm including it here is because I feel it's helpful in understanding what's going on here. But if you don't like it, if you don't think this code snippet is helpful in that way, then ignore it. But you definitely need to know how to do problems like this. Okay. Okay. Next, we'll get the next topic.